Okay, let's start with the new topic of non-deterministic finite automata with null transaction. Previously, we have seen the introductory concepts of NFA, and then at the end we saw that how can we convert a NFA into an FA, um, into a NFA using subset construction method. And now we are going to see that uh, how null transitions can be involved in NFA, in union concatenation and its clean star. And then we will see how can we convert an NFA null to an FA simply. And then we will see the definition of null closure of a set of states with an example. Um, and then finally, we will see the Kleen's theorem through which we can convert um, different FAs and finally into, um, for example, we will be given with two FAs and then we will convert those two FAs to NFA, and then we will see that how can we convert um, or we can build an NFA finally with the help of irregular expressions. So we have to basically build an NFA null for a regular expression, and we will take some examples, and then we will conclude this lesson. So let's start. So the first is we have to get some concepts about NFA with null transitions. For example, here on the left hand side, we are seeing that we have a uh, we have a NFA with two states. Starting state is Q0 and the accepting state is Q1. So after taking 0 from Q0, we are reaching at Q1, and then we have a loop at Q1 with label 1. So the edges are not complete here. So that's why it is NFA. And same is the case. And this left hand side NFA is uh, an NFA which is accepting strings 0 and 1 star. So this is 0, 1 star. This is the regular expression, are the strings you can extract from this regular expression, and then those strings will be accepted by this left hand side NFA. And the language uh, for this NFA is written here. And similarly, on the right hand side, we have a another NFA starting with P0 and P1. So we have a loop of with 0 at P0, and then we have an edge with label 1 and going towards the final states P1. And the language for this NFA is 0 star due to this loop and then 1. So it is written here. And if without, so there is no null transitions involved in these two NFAs. So if we want to concatenate this L1 and L2, then it will become like this one. So this is the first portion. Maybe I can use this annotation. Here you can say this is the first portion, and this is the second portion. This is the NFA for L1, and this is the NFA for L2. And we want to concatenate this L1 and L2. So you can see that from the final state, you can draw an edge and it is with 0 and 1. So any symbol can come. And after taking any symbol, input symbol 0 or 1, we can reach at P0. And then we can also, for example, this is concatenation. And then from Q1, we have another edge labeled with 1. I can change the color so that it will not be issue. So we have another edge here, which is reaching at state P1. And this edge is labeled with 1. So now consider it is a concatenation. So concatenation of this L1 and L2 becomes 0, 1 star, 0, 0, 1 star, and then 0 star 1 as written here. 0, 1 star and 0 star 1. So what is the minimum strings then? So this can be null, this portion can be null. I can again change the color. So what I'm saying that this portion can be null. So what is the minimum string? 0, 1. So from starting point, taking 0, I am reaching at Q1 and then taking 1. If I will take here 1, then I will reach at P2 and it is not a final state. So I will take this edge. And after taking 1, I am reaching at P1. So this minimum string is then accepted. So that's why this edge as highlighted with blue line is necessary. And then think over some other strings. For example, 0 and then 1, 0 and then 1. If this is a string, then 0, maybe I can take 1 and then 0 and then finally 1 and I am reaching at P1. Or I can reach 0, 1, then 0 and then 1. So both ways, in both ways. So that's why this edge with input 0, comma 1 is needed. So this concatenation in which there are no null transition are involved. So you can concatenate these two NFAs using your previous knowledge, maybe in some lecture during the discussion of FAs, or you have to do it logically first by combining the regular expressions of both L1 and L2, and then you have to think of different strings, and then you can draw the final NFA for L1 and L2. So this is something practice that you have to do. And we are discussing these things because we have to start another topic next. And for that one, we are just taking a little bit background so that then we can claim that this is something a complex problem and you can solve this problem easily by using some other approach. So anyhow, this is the concatenation example, and if you want to take a union between this L1 and L2, so this is L1, this is L2, 0, 1 star, and then 0 loop and 1. So union, so this is, as you can see, so this is 0, 1 star, L1, and this is 0 star 1, which is for L2. And now we have to take the union. What is meant by union? So again, you have to take the union of for these two regular expressions, 0, 1 star and 0 star 1. So you can apply the U symbol between these two regular expression and it will become like this one, 0, 1 star union 0 star and 1. So now if this is the situation and you have drawn this L1 and you have drawn NFA for L1 and L2, so what is the minimum string here? Either this part can be taken, either this part can be taken. So then it can be null. So only 0 is one part. So if it is only 0, then this is my starting state labeled with this arrow. So 0, I will take 0 and I will reach at Q1 simply. So it is accepted. And if 1, so I will take, so uh, that's why from initial state Q0, I will take 1 and I will reach at P1. So that's why this label, so that's why this label is needed. So that's why this label is needed, because one minimum string 1 is possible from this regular expression. And then you have to maybe think this can be null 0 and this can be null and 1 from here. So okay, so then from initial state, if 0 1 is the minimum string, I can take 0 and I can apply 1. So this is one way. Or if there is 0 and if it is null, and if it is again 0 and 1, then okay, 0, for example, the string is 0 0 1. So then 0 and there is no further 0, so this path is not valid, this path is also not valid. Then this path 0, then again 0, and this one, so that is then the valid path. So that's why this edge is also needed. And in this way, you have to think and you have to design the union for L1 and L2. And so then finally you can say that this NFA is accepting this regular expression, which is the union of your previous two NFAs. So now I can clear the drawing. So what I want to say, actually I want to say that if you have to take concatenation of two NFAs and the union of two NFAs without null transition, then this can be a little bit complex design for you, because then you have to think different possibilities, and then it will take time. So is there any mechanism or is there any other approach which would be quite easy, and then we can design this concatenation and union quite easily? Yes, there is another approach. That approach is by using null transitions. So we can do the concatenation or we can do the union uh, by using the null transition. And then this approach of designing concatenation of two NFAs or union of two NFAs will become easy. For example, here, so this is an NFA accepting 0 1 star 0 star 1. So which is the concatenation of this one. These are the 0 1 star 0 star 1. So these are two L1 and L2. What is the concatenation? Concatenation is 0 1 star 0 star 1. So 0 1 star 0 star 1. So now if you have to concatenate two NFAs, then it is a quite easy approach that this is something L1 and this is something L2. So you can concatenate two NFAs by drawing an edge from the final state. This is the final state. From the final state of L1 to the initial state of L2. And then you have to draw an edge and label it with null. Or you can introduce that um, edge with label null, and then all the strings will be accepted as you saw in the concatenation here, as you saw in the concatenation here in this previous complex method. So this method is quite easy because you are given with this NFA for L1 and an NFA for L2. What you have to do, you have to simply draw an edge from the final state of L1 to the initial state of L2, like this one. Uh, And after drawing that edge, you have to label it with null, and then it will accept all the strings. These strings you can check it by yourself. For example, 0 1 0 1 is a string, then 0 and then 1. So null is something that you will automatically, you don't have to take some input symbols. So, so this now becomes a string, so you don't have to take any special symbol. Null will automatically uh, make you able to go forward to the next state. So that's why then you will reach at this P0, and then after again take 0 is here and then 1 is here, then your string will be accepted. So this is an example of concatenation with the null transitions. Okay, let's move on to the next. And if you want to take the union, then what you have to do, so, and then I have finished the status of the final state for L1, and I have kept the uh, final states of L2 as it is, because in concatenation, if you remember from my previous lectures, in concatenation, uh, final states of L2, because this is the concatenation, and in your concatenation you know that um, the final status of NFA1, like this one, will be vanished, and the final status of NFA2, which is for L2, will remain as it is. So so which is truly the status of the you can say the final NFA for L1 and L2. Okay, and if we want to take the union, what you have to do, uh, so what you have to do, so this is, for example, here you can say this is your L1 with Q0 and Q1, and this is your L2 with P0 and P1. So what you have to do for the union of two NFAs, you have to introduce another state, which would become the initial state then, and then you have to draw uh, an edge with null towards the initial state of L1, and then you have to draw an edge with label 1 to the initial state of L2, which is for the NFA2. So this is quite easy. So what you have to do, you have to introduce another state, and then you have to make that state an initial state. And then you have to draw two edges with null transition towards the initial states of the NFAs. And then this becomes the union. So 0, 1 star union, 0 star 1. So this is the regular expression that you have already seen. So this is now quite easy, because now you don't have to think too much. You can simply draw the null transitions, and then you have your union and concatenations in front of you. Okay. So now we will see the definition of the, now we will see the definition. So, okay, here comes the definition of NFA. We already know the definition of NFA, but now we are again seeing the definition of NA, but with null transitions. So the definition is very much similar. Only an extra thing is the insertion of null into the set of alphabet symbols. So a NFA with null transition, which is NFA null, is 5 tuple with Q, sigma, Q0, A, and delta. We know all these things, where Q and sigma are finite sets. Q is a set of states of NFA, and sigma is the input symbols, set of input symbols are finite sets. Q0 is the initial state, which is from the set of states, and A is the set of accepting states. That's why it is written as subset of Q, because it is these are also states actually coming from the set of states Q. So then delta is very much similar. Q cross sigma implies 2 raised power Q. This is the definition of NFA we already have seen in previous lecture. So what is the difference? Difference is only this one, this null transition. So you have to introduce this null transition along with this sigma. So the input symbols can be input symbols from this set of sigma union null. So now what it is saying, it is saying that if my input symbols are 0 and 1, so my NFA will can take 0 or 1 or null. So that's why this is the only extra thing null in the definition of um, NFA with null transitions. So now we will see an example with some strings to clear the concept, further clear the concepts of this NFA, concept of this NFA null. So for example, we are taking string 0, 1 and suppose that this is some NFA for this string. So starting state is Q0. We are taking 0 and then we are reaching at R. And if it is null, we can go forward to S by taking this null. Even null is not the part of that string, but null, as I said earlier, null make us able to go to the next state automatically or implicitly. So from this S, we will take this null and we will reach at T. And then this one, which is the part of that string. After that, we will reach at U, and this null will make us possible to reach at F automatically. So then we can reach at F automatically. And then 0, 1 string is accepted here in this NFA with null transitions. So this is the example. Now the next topic. This topic is we want to convert a NFA null to an NFA. And now you can understand that NFA null is something, an NFA with null transition. And then we have to remove these null transition, and then you have to finally obtain a simple NFA without null transitions, maybe. So for example, here you are seeing there is no null transitions. So, okay, so this is now the NFA null which will be given to you that you have to convert to an NFA. So this is given to us, there's a loop of 0 and then null going to B. From B we are taking 0 going reaching C. From C we are taking 1 and reaching B. From B we are also taking null and reaching D, and there is a loop of 0 here. So this is an NFA and it contains null transition, so that's why it is a NFA null. So if you want to convert it into NFA, what are the steps? You have to build a transition table. So when you will build in a transition table, then the transition table will contain input symbol 0, 1 and null, because now null is the part of the NFA null NFA null of this NFA. So now there are three symbols, 0, 1 and null. So that's why let's go to the transition table. So this Q is for to represent states, and my states here are A, B, C, and D. So A, B, C, and D are here. And first transition from any state with null where I will reach is mentioned here. Transition delta means transition, single transition. And then transition from any state to with 0 where I will reach, it is mentioned here. Transition from any state with 1 where I will reach, it is mentioned here. For example, at A, state is A, and when I will take null where I will reach, when I am at A, if I will take null where I am reaching at B. So you have to mention this B here. And then at A with 0 where I will reach, at A with 0 where I am reaching at A. Okay, I am reaching at A, so you have to mention it here. And at A, after taking 1 where I am reaching, no, I don't have a transition with 1 here, so that's why it is null. It means empty or something. This is phi, which is phi, which means empty something. I am not saying null because then you maybe you can mix this concept with this null. So this is empty. So now I have to check from state B. So from B, if I will take null where I am reaching D, so you have to mention it here. From D, from B, if I am taking 0 where I am reaching C, so you have to mention it here. From B, if I am taking 1, no, I don't have a transition. So it is again phi empty. Okay, now I'm going towards this final D and I am skipping this C for you. Or you can, or we can continue this C and then we will skip this D. So from C, I don't have any null, so it is empty. And from C taking null, I don't have, so empty. From C with 0, I don't have, empty. From C with 1, I am reaching at B. So empty, empty, B. So empty, empty, B. That's why it is mentioned here. So this is the transition. So this is the transition table with the single transition on input symbols. Now the other step, second step is that you have to draw another transition table, and this would not be single transition. It is delta star, which means multiple transitions, more than one transitions. But now you have, because null is something extra, and now you have to leave the null transition. You have to leave to mention the null multiple transitions here, because null is something which make you able to automatically go forward to the next state. So that's why in this transition table you don't have to mention null. So that's why we are only mentioning multiple transitions on any state with input symbol 0, or multiple transition on any state with input 1. So this is same, all states. So now you have to listen my words carefully, because we will take this input in input 0, but it can happen during an FA that after taking 0 or before taking 0, null is coming. And if null is coming, then we can automatically go towards the next state. So you have, and then if you are going towards the next state, then you have to count all those states here in this transition table. So for example, at A with 0, what are the multiple transitions? So down, okay. At A with 0, I am reaching at A, but this null is making me possible to go forward to this B. So A is with 0 is possible, but null is making me possible to reach at B. So B is also accessible from A with 0 input. And now I can also take first with this null, and then I can reach at B, and then I will again take this 0. I am ignoring this loop with 0. I am taking null first, and then I am taking 0 here, and then it make me possible to reach at C. So C is also possible from A with 0 input. Okay. And now again, I am at A and my string is 0. So I will first take null reaching B, and then I will again take null reaching D, and then I will take 0. So it is also possible from A to reach at D. So now you have seen that from A, if I have a string 0, then I can reach at B, C, and D. So that's why you have to mention this A, comma B, comma C, comma D here with 0. And with 1, now I have to check. With 1, now my string is 1. So this is something not possible, but this is possible. Null, I am reaching at B. You have to consume your, keep this thing in your mind that you have to consume your string. If your string with 0 or 1 is consuming by taking some null transition, that is okay. Then all the states in the path are accessible. But if your string is not consuming, then you cannot consider in between states. So anyhow, so from A, you are taking null. I cannot take this 0 because my string is 1. So this path is also not possible. I can take this null. Okay, I'm reaching a D. But again, this is 0 and I have to consume what? I have to consume 1. So this is now again not possible. So from A with input 1, no any state is accessible for me. So that's why you have mentioned phi here, empty. Now for B. And now for B and my input is 0. So I am here at B. My input is 0. With taking 0, I can reach at C. That's fine. But I don't have a null so that I can reach again here and then here. So, okay. So C is accessible, okay, because now string is consumed, 0 is consumed. From B, I can take this null and then I can consume my 0 here. So C and D is possible, so which you have to mention. So this is mentioned. And from B with 1, from B with 1, 1 is not possible. Okay, null and then 1 is not possible. So that's why it is empty. So it is empty here. And this is something you have to think by yourself. So in this way, you can uh, uh, complete your transition table for multiple transitions, delta star or clean star. And now, if after making these two transition tables, now you can draw your NFA uh, without null transitions quite easily by looking over this second transition table. So for example, this is A. So first draw the A. So A is drawn. And from A with 0, you are reaching at A. So you have to draw the loop. From A with 0, you are also reaching at B. So from A with taking 0, you are reaching at B. So you have to mention it. Or I can use the annotation. So, okay. Let's do it now. So from A with 0, I have done with this B. From A with 0, I can also reach at C. So from A, I with 0, I can draw an edge towards C. From A with 0, I can reach at D. So okay, from A you with 0, you can draw this edge. So all four edges are now finished, which is representing this one. And from A with 1, it is empty. So there is no need to mention any edge here with 1. Now from B with 0, I can reach at C and D. So you have to draw two edges. So from B, you with 0, we can go towards, I can change the color. I can go towards this C or to D or this one to D. So both edges are complete. And from B with 1, I don't have anything in the transition table. It is empty, so you don't have to draw any edge. Okay, then from C with 0, it is empty. I don't have to draw any edge from C with 0. And then from C with 1, I can reach at B and D. From C with 1. So from C, I can draw an edge with 1 towards B, and I can draw an edge with 1 towards D according to this transition table. And then from D with 0, I can reach at D. D with 0, I can draw this edge like this one. And the second is empty. So this is now, your NFA, and this NFA is not containing uh, any null transitions. And now after making or drawing all the edges, you have to mention the initial state and the final state. So initial state is the initial state from here, which is A. Oh, and here the final state is D. So initial state is something same, A. But, and D is the final state here. So you can also mention D is the final state here. But now this is something extra information written here on the right hand side. A becomes, I have to mention this A, which is initial state, as a final state also, because A becomes the final state since null is the minimum string in the language. When I was doing this, when the null was the part of this NFA, then D was the final state. But if null is the part of this given NFA null, then it means that at initial state I can take a null and this is my final state. Also, if I don't have any input symbol in the string, then by taking null I can reach at A, and A is my final state. So that's why you have also, if null is the part of your given NFA, keep this thing in your mind. If null is the part of your input symbols like this, or if null is a part of your input symbol for the given NFA, then you have to make your initial state also a final state. So that's why this A is initial state and also the final state. And now this is my NFA. And if I will say that convert this NFA to AFA, then from our previous lecture, we have seen the method for construction of NFA to AFA using subset construction method. So then at this step, you have to use that subset construction method, and then you can convert this NFA to FA, and then this question will become a little bit lengthier than your previous approach of subset construction method. So that's why it is written here. Now FA from previous procedure becomes as given in the next book. So if I apply that previous subset construction method that you have to do by yourself, then I will get this FA finally by using that subset construction method. So you have to do this step by yourself. And now we are reaching at another definition, which is the definition for the null closure of a set of states. So we have to see what is meant by null closure of a set of states. Let's see. And with some class, it was also a question to me that kindly explain the null closure of a set of states. So now here it is that explanation which was asked at some spot, anything I don't remember. So here is the explanation of that null closure of a set of states. So suppose this M is equal to Q sigma Q0 A and delta. Suppose this is an NFA null. We are in between the topic of this NFA null. So mostly we are using NFA null most of the time, because as far as the NFA is concerned, in previous lecture we have studied some things about simple NFA, and now we are studying something about NFA-NULL. Okay, so you have to keep this thing in your mind. So if we have some machine containing 5 tuples, and if it is an NFA-NULL, which means in the input symbols, uh, there could be some other symbols, but null is the essential part. And let S be any subset of Q. So this Q, so I can use this annotation. So this is my Q, which is a set of states. And now we are supposing that S be any subset of Q. So we are taking some small number of states from this bigger set of states, which is Q. So this is small number of states, and this Q is the set of states for the NFA-NULL. Then the null closure of S, this null closure of S is the set. We can represent the null closure of S with null of S, nothing else. So null closure of S is the set null of S. So mathematically we can represent this theoretical statement null closure of S with null of S. And we can define this null closure of S with these 3 points. What the null closure of S will contain? So, for example, we have said previously in a theorem that regular languages are closed under union, intersection, and complement. So what it means? It means that all the regular languages, we can take union of them, we can take concatenation between them, we can apply the complement operation between them. That's why it is the all regular languages are closed under union, concatenation, and Kleen star operation also. This is the theorem. So now this is some kind of the same word but with different concepts. So I can say S is closed, S is closed, S is closed for this Q with these 3 things. And when I will say closed, in our previous lecture, it was union, concatenation, and something, but here it is 1, 2, 3 mentioned here. So if I say S is closed, or null closure of S, this is the same sense. So null closure of S is the set null of S, which we can define as like these 3 points. What these points will contain? For example, every element of S. For example, I can write Q. I can write Q as Q is equal to Q1 Q. Sorry, but I don't have something better than this with me. If this is my Q and my S is, for example, only Q1 and Q4. So now what I am saying, every element of S, for example, Q1 and Q4, is an element of null of S. What is null of S? Null closure of S. So this is S. Let S be any subset of Q. The null closure of S is the set null of S defined as follows. S will contain some states, and null, if you apply null closure on S, then it will also contain some states that I can call it a set. So here I am saying every element of S, here S is containing two elements Q1, Q2, is an element of null of S. So I know that when I will apply some null of S, then it will again contain some state that would be these states. So that's why the first condition will always be true. Every element of S is an element of null of S. So null of S is something at the moment we don't know, but we are saying that every element, here I have Q1 and Q4. So that's why Q1 and Q4 would be the element of null S also. So you can keep these same elements here in null of S also. Okay. Number two, these are the rules actually that you have to keep in your mind. And after keeping these rules, if these rules are okay, then you can say finally that null closure is okay with this set of states S. Number two, for any state Q belongs to null of S, null of S is what? It is same, these Q1 and Q4. And if I am taking Q1, then if for any state Q belongs to null of S, it has two states Q1 and Q4. And if I am taking Q1, then every element by applying single transition, delta Q comma null. So if I am at Q1 with null and null is giving me access towards other states, maybe I can reach on Q4 using null at Q1, or maybe I can reach at Q1, I can reach at Q2 using this null. Then the states on which I am reaching, which is Q2 and Q4, is again uh, he's saying, this statement is saying that is again the states that I will get would be, you have to include those states in null of X, in yeah, null closure of X. So again, I want to explain this statement that for any Q, for any state belongs to null of S, if this is my state, if my S is like Q1 and Q4, and if at Q4 and after taking null, I am reaching at some state, and if that state is Q2, then I have to include that state Q2, then I have to include that state Q2 in null of S, in null closure of S. That is the meaning of this statement. And if my S is containing Q1, and if I apply the, and from Q1 there is a transition towards some other state with this null, and I am reaching maybe at Q4, then I have to include, then that Q4 is included in the null closure of that set S. This is the meaning of this second statement. And in this way, I can get different states in the null closure of X. And that is called actually the null closure of S, or null closure of a subset of Q, you can say. Number three, no other element of Q are in null of S. So only the transitions from some state or I can rephrase it as from some state, only the transitions with null which is making us possible to reach at some other states, only those states would be included in the null closure of S. That is called the definition of null closure of a set of states. And I hope that now you will understand. Okay, now moving forward towards the example. now we are going to see that what will be the effect of null, or we will execute some strings by using this definition of null closure. Example delta star. So this is now our NFA. So it is Q0, we have a null P reaching P, we have a null reaching T, and then 1, 0 loops, null coming back to this Q0 and so on. You have to keep this NFA null in your mind, and then we are going to apply some operations over it or strings over it. So first delta star Q0 null, which means that I am at initial state Q0 and I will take this symbol null and I will apply multiple transitions. So I have to use multiple, I have to process multiple transition. How I can write it in null closure? So I am checking basically null closure of this state Q0. I am checking basically what? Null closure. I am checking null closure of this state Q0 according to my previous definition. Okay, that's fine. So null of Q0. So now I have to I have to see that at state Q0 after taking null on which states I can reach, and then I have to mention those states here, and that would be my possibilities. So I am at Q0, taking null I can reach at P, and after that I don't have anything, so only P. At Q0 input string is null, so I can take null and I am reaching at T, and this is opposite direction, so only P and T from Q0 is possible, which is meant. So Q0 and P comma T are the possibilities which is mentioned here. Okay, so this is now my null closure of Q0. Okay, I hope now you will understand. Now again, delta star Q0 and 0. Now I am taking a string 0. After that, I am taking a string one step ahead after this null. So delta star Q0. So I am at Q0 and I am taking this string 0. And now I have to see that on which states I can reach, but now I have to consider null implicitly, which means automatically, according to the definition of my previous knowledge or null closure. Okay, so I am here. By taking this null, I can reach at P, but then I can take this 0 and I will remain on this P. And my string is consumed. After that, 1, I don't have 1, so I will remain here. With Q0, I will take this null and I will reach here. This is not possible because my string is 0, so I will take this 0 and I will reach at U. I will reach at U. So this P, T, U, these are the possibilities, but let's see that. So delta star Q0, delta star Q and comma 0. So I am at initial state Q0 with input symbols 0. So what is the null closure? So I have to find the null closure of Q0. I have to find the null of Q0 not, because this is not null mentioned here. So I have to find the null closure because this is example of null closure. So the null closure of this thing, because now my symbol is changed here, according to the NFA given on the next page is, I can write delta uh, P is any state here. This is something not according to the uh, NFA given. This is, for example, given here, this P means any state. This Q means any state. This P is the P which is this one. So this P and this P is same, which means any state, because this is some formula according to our previous lecture when we have seen the recursive definitions for NFA. So that is that recursive definition example. So this is my current, I can give you the understanding. So what is my last string from the right? This 0. So this 0 you have to mention with any state P, and it is only single transition. So that's why there is no delta star here, only delta. And before that, before this 0, what are the possibilities? Before this 0, what are the possibilities in this NFA? This is 0, and but before that null is possible. Here it is 0, but before that null is possible. So this is the understanding. So this previous transaction that you have seen here is basically the previous step of this one, which is mentioned here in this format. This is delta star, I can say any state and then null. So delta star Q is any state with null. So this is my previous process. And then after applying multiple transitions with this null closure, I will reach at some state, and that is called P, and that P is mentioned here. This is the understanding of this equation. So this is the current state according to this symbol, last symbol from the right. And this is something that you have to apply the transition with 0. That is only a single transition. But before that, there would be multiple transitions. And if there would be multiple transitions, then it is possible that you will reach at multiple states. So that's why you have to take the union according to the recursive definition of NFA in previous lecture. So let's now clear it. So this is something, the formula, and then you can write the null closure. I have to find the null closure. So now move on. Previous, when you applied null on Q0 according to this NFA, which is mentioned here, this is my previous step where I read at P and T. And after P and T, I can apply this 0, I can apply this single transition. So, okay, so what I can write now, null, and then can I write PT. So I have a transition from delta, this PT. These are my previous states, or I can apply delta at Q comma 0. So this was my set previously. Okay, I have to annotate it again. When I will make annotation able, then my movement of pages normally stopped. So this is my previous states, our previous states, which is equal to this one. And then I have to apply the 0 on states which I will obtain from this previous states. So now try to understand. I have to apply this 0 On which states? On states P. And where I am getting this P? From this previous step. And what I got in my previous step? These states. So I have to apply 0 on this one, that one, and that one. So that's why it is mentioned here, null delta q0 comma 0 union delta this p comma 0 this t comma 0. So this is my, and this is the union. So now I hope you will understand. I have to close the annotation. Okay, now I am here. So at q0 with 0, at q0, do I have something? You can do by using any combination. However, with 0, I don't have exactly, it's a single transition, not multiple transition. Look at it here. I only mentioned delta, not delta star. If I will mention delta star, then this is the possibility that I will take this null first and then I will consume this 0. But here only delta single transition is mentioned. So, okay, at Q0, do I have a transition with 0? No. So that's why it is empty. Then union delta P0. So on P, I have this 0 and I will again reach at P, and that's union T0. So at T, I can reach at U. So that's why U is here. And then null of this is empty, only P and U. PU is mentioned. And so finally my set with 0 string is PU. You have to keep this thing in your mind. So with only null, I have these states. With 0, I have now finally these states. Now delta star, multiple transition with Q comma Q0 and the string is 0, 1. So now what it means, okay, see it again. So now from the right hand side, only the last symbol. This is mentioned my last symbol, last transition, delta, any state P and with 1. And previously, previous is this 0. This is null and previously delta star Q0 with 0. All the input symbols here on the left hand side, you have to mention all those symbols here. So from Q0, all those input symbols and delta star, multiple transition. And then where I will reach at P, and that P is mentioned here. Okay. So you have to write 1. And previously with 0, what you get in the previous step? If you look over here, Q0 with 0, this is something you already have done. Q0 with 0, you already have done, and you got this P and U. Okay, so P and U. So delta only last transition, null into again delta P and U. P with 1, union delta U with 1. Okay, and then null P with 1. Okay, check it. I have to clear the drawing. So P with 1, I am reaching at R. U with 1, I don't have any edge, so empty. So P with 1, I am reaching at R. Okay. So 1 is empty and other, I am getting something from here. This one is empty. So only R and finally R. Now I am enhancing my string. Delta star, I am taking another string. And then you can see the things by yourself. This is now my last input symbol, and this is something, the remaining. So null, so this is something you mentioned here, any state with 0, single transition, and this is something you mentioned here with any state Q0 delta star, I will reach P, which is mentioned here. And this is with 0, 1, you have calculated these things here, and I have got only R. So null delta R comma 0. That's why this is written here, R with 0, which I have to check now from my NFA, R with 0. So this is my R, and with 0 I am reaching at S. And as, so I am null into, I am reaching at S. Now I have to see in the null closure finally. Now this is the step of null closure. Okay, I have mentioned here, it is null closure. This is null closure. So I have only single state S, but now I have to see the null closure. So look at, now find the null closure. So I am at S. With null, I can reach at W. With null, I can reach further at Q0. With null, I can reach, no, this is the opposite direction. So this is not possible. So S, W, Q0, and from Q0, I can reach at P, and I can reach at T. So 5 possibilities. So S, W, Q0, P, and T. So this is something I will get. So this is the null closure. This is finally the null closure. You can also check this null closure for this one, for this one, and all other previous things. But I mentioned only in this last portion because it is attached here with this one, but you can also check this null closure here and also here, and you will get nothing. That's why I didn't discuss this thing at that time. So anyhow, now I hope that you have the complete understanding of this null closure. And now the last part, Kleen theorem. And what is Kleen theorem? Number one statement is saying that every regular language has an FA. Okay, we know that from the day one when we studied regular languages. We know that regular languages have their machine as FA, or NFA or DFA or whatever. So this is Kleen's theorem. And the number two is just the rephrasing of the first one, is that every FA has some language and that language is the regular language. So this is nothing anyhow. Move on to the next things. And we already know that regular languages are closed under union, concatenation, and Kleen star. We know this concept, union, concatenation, and Kleen star. Kleen star is the kind of multiple iterations, the same concept as the concept of this star. This star is in your regular expressions. So for example, just quickly, because this is something you already know, if L1 is the language and FA1 is the FA for it, and L2 and we have a FA2 for it, we can get L3 and we can get an FA3, and we can say that this L3 can be the union of L1 and L2 if we want to take union, and this L3 can be concatenation of two languages, L1 and L2, like this one, this L3. Or we can say, if there is an, so this is union and intersection in mathematical form. And number two is if we have an L1 like this one and FA1, and if then we will get L3 and FA3 according to these same conventions. Otherwise I can write L2 and FA2, but then you will mix that L2 with this one. So that's why it is L3 and FA3. And that, and here L3 is something what, which is a Kleen star of this language L1. Okay, now this is something theoretical stuff, and now we will see the practical concepts of not exactly practical, but in drawings, practical in drawing perspective actually. So now we will see these things in our design actually. For example, if we have two FAs, FA1 and FA2, and if we want to take a union between them, then we will get another FA that is called FA3. For example, this is FA1. You are here, seeing here, initial state, final state, and taking strings A and B. So this is not exactly FA, this is NFA actually, because we are discussing the concept of NFA. So this is AB, which first string AB, this is FA1, first string AA, we have an FA2. And if we want to take union, what you have to do? You have to introduce, I can use annotation. You have to introduce another state, the new state, and you will make the state as initial state, and then you have to draw two labels. For example, here I have to make state, and then I have to draw two edges to these FAs with null transition, as you are seeing here, with null transition. And this is what you are doing. This is, you are making a union of two FAs, and this is something we already seen by adding another initial state with null transitions. Okay, now, okay, in this way you can take the union. Now moving on to the next, and if we have two FAs, FA1, FA2, if we are doing a concatenation between them, then and we are getting FA3, yes, we can get FA3 if these are two FAs, this one and that one. What you have to do, we have to draw an edge from the final state to the initial state of the second NFA, and then we have to change the status of this final state to normal state, and this initial state to normal state. And now this is the initial state, this is the final state, and you can introduce null here. So this is the method through which you can concatenate two FAs. And if you have more than two FAs like this one, maybe there are some FAs here and these are the final state, and maybe there are some states here and these are the initial states. What you have to do, you have to introduce another state, and then you can draw the edges with null transitions between them, and then you have to remove their status too with the same concept. And in this way you can concatenate more than two FAs in a similar way. So this is a concept which is not difficult one. Now move on, and if you want to apply, if there is an FA1 and if you want to get FA3 or if FA1 and then star, then this is called FA3. This is basically the explanation of these things: union, concatenation, and then now L3 is equal to FA, L13. So we are explaining in terms of design. So FA1, and this is, you can say L3 is equal to L1 star. Okay, so if this is an FA for FA1, and if we want to make it as a clean star, then what you have to do, you have to introduce again another state. You have to introduce again another state with null transitions. Then you have to make it plus minus. This is the initial state. You have to, this is my initial state and this is my initial and final state also. You have to draw an edge from here because this is loop star. So that's why you have to draw and you have to remove the status of final state here. Then you have to draw an edge with null to the initial state so that it would be a star, this to represent this as a star, clean star. And then I have to make null edge here. So null, initial, and in this way you can convert any FA to its clean star format. Okay, that's fine. Now we are going to see some, we will apply these concepts along with some other concepts on this topic. And this topic is about building NFA-NULL for a regular expression. Uh, so this in a question, a regular expression will be given to you and you are asked to build a NFA-NULL for this regular expression. So for example, this regular expression is given to you and you have to build an NFA-NULL over it. Then what you have to do, you have to first think that what are the input symbols in it. So input symbols in this regular expression involved are 0 and 1. Or you have to think the minimum strings. Minimum thing 1 is possible and also 0. So it is always better to start with the input symbols first, and then you have to think in these terms. You have to think in terms of parts actually. This 1, 0 is something, a part which cannot be altered, but this, due to this plus, you can get this part and you can also get this part and then clean stuff. So we have to build NFNL. So what 0 and 1 is the input symbols. So for 0, what would be the NFA? So this is initial state. After taking 0, I can reach at final state and I am labeling it. I am saying it with R1 and it is for 0. And for 1, initial state, taking 1, I am reaching at final state and I am calling it R2. This is for 0 and this is for 1. This is something you have to draw by on the input symbols. And after that, if I concatenate this R1 with itself, then what this machine would accept? It would accept 0, 0. So I am going to concatenate this R1 with R1. So this is my first R1, this design, and this is my again R1, and I am introducing uh, a null transition from the final state of R1 to the initial state of R1, and in this way, what would be the string that will be accepted by this uh, NFA R? I can label it with R3. So it will accept 0, automatic transfer 0. So for string 0, 0. And what is this 0, 0? This is that one. I said it to you that you have to first think for the minimum strings, for the minimum input symbols, and then you have to build your NFA according to the parts. These are the parts. For one, I have this one, R2. R2 is for 1. And for 0, 0, this is something R3, which I obtained here. So now if I will apply the union between this 0, 0 and 1, this is 0, 0, this is 1. And if I will apply the union between these two NFAs, then I will get something for this inner portion. Okay, I am going to do it. Okay. So this is for 0, 0. And I can also make something for 1, 0 just, and for 1 this is 1 and this is 0 and I am going to concatenate it. Now 1 introducing null and then this 0 by concatenating R2 and R1 I am getting R4 and this NFA is for 1, 0, that part on the right hand side, 1, 0 star. Okay, that is also something you have done. Now I am going to do something for 0, 0 plus 1 for I am going to do this one, inner part. Okay. So for 0, 0 and plus 1, what I have to do, this is something I have for 0, 0 and this is something for 1. What I have to do, I have to apply the union. And how can I apply the union? I have to introduce another initial state and then from that state I have to draw a null transition to this one and null transition to this one, and in this way union will be occurred. That is perfect. Okay. Here R5. How can I get R5? This is my R3 and this is my R2, 0, 0 plus 1. So R5 would be equal to R3 plus R2 by taking union between R3 and R2. So this is something 0, 0, and this is something 1. After introducing initial state, drawing null transitions, I am getting R5. Okay, and what is the next step? This is R5. Next step is taking clean star. And how can I get clean star? By applying this concept. And union is, concatenation is this step, union is this step I discussed here. So clean star, clean star. How can I get clean star? Clean star is simple. Introducing another state, taking edge back to that one and introducing that edge. Okay, I will do that. So this is my R5 and I have to take clean star of R5 according to this regular expression. So what I can do, I have to introduce another state here. This, okay, this state is at this position. Okay, I have to take some another color. This state is something here and the rest of the design. So I have to introduce another state, and then from its final state, I have to draw edge to that state. So that is that edge, and similarly that edge with, so all these new edges are null transitions. So null transition, null transition, null transition, and in this way this clean star is. So R6 is simply taking R5 and then star, applying clean star concepts, applying the concepts of clean star. Okay, so this is something, this part is now finished. 1 0 star. So now taking clean star, 1 0 is where? This one, R4. So I can introduce new state and then getting edge back, and then this one I can get after taking clean star of R4. So this one, introducing this one, R7 is taking clean star of R4. And what is the final step? I have to apply the concatenation of this, which is R6, and this is R7. So this is the concatenation. Okay, so I have to apply the concatenation of between this R6, that one, and R7, that one. So, okay, which is this one. R8 is R6 and R7. So this is R6 and this is R7, this one. I can, this annotation is always a problem on Zoom. So this drawing is mentioned here in the lower part of this diagram. And from, it is a concatenation. So concatenation is simple. What you have to do, you have to take edge from the final state of the previous diagram towards the initial state of the next diagram. This one also the initial and the final. That's why maybe edge is consuming. So that's why mentioning plus minus is better than doing double circle here. So I can. So you can say this is initial state and also the final state. This is initial state and also the final state. So that's why you have to draw the edge from the final state of the first diagram towards the initial state of the second diagram, and it is represented with null, and this is the concatenation. Okay. There is another step that you can remove these so many null transitions. And this whole process is mentioned in the book, that how you can remove extra null edges from a diagram. So you can read that topic from the book by yourself and try to implement over these examples. And that's the end of this lecture. Thank you very much.